Ah. Today, our first speaker is Miayet Pasha. Miayet is a postdoctor at Arizona State University. She will present her work titled Modulus-Based Iterative Methods for Constrained LP2LQ Minimization. Thank you.
Hello, everyone. Thank you, organizers, for the opportunity to give a talk and for organizing the series of these very nice lectures. Today, I'm going to talk about some joint work with my advisors, with Lotte Reichel at Mathematical Department at Kent State University, and Alessandro Buccini, that is an assistant professor at University of Cagliari in Italy. So today I'm going to talk about the modulus-based iterative methods for constrained LP-LQ minimization. As an outline of my talk, I'll first introduce the kind of problems that I'll be explaining and talking about, and then I'll go briefly over the LP-LQ regularization method and a little bit about modulus-based iterative methods, and then after that I'll talk about the main contribution of this paper about the constrained LP-LQ minimization method, and then in the end some numerical examples will illustrate the method that I'm going to talk about. To start, the mathematical problem setup is going to be written as a simple linear system of equations, AU equal to B, where the matrix A is an ill-conditioned matrix that models the forward problem. U are the desired parameters or the solution that we are looking for. B are the observed data or the measurements that we get during the process. And B true will be the data without noise that is not available. So in general, we do not have the data without noise. And E is the noise. I want to stop a little bit here and say that the noise can be Gaussian, it can be impulse noise, it can be a mix of them, and so on. So, and this talk is mostly dedicated to this case where you have different applications where your noise might be Gaussian, and the method that we are proposing can solve it. But also, if you have other type of noise that might be very difficult for other methods, then we propose a way how to solve this kind of problems. And the goal is, given the data B and also some information about the forward model, we would like to compute an approximate solution for our desired solution. So, and a simple example of this kind of problems that can be written as linear system of equation is, for example, image deblurring. For example, let's look at this picture over here. We have an image that is blurred and also noise contaminated. And the goal is to find an approximate solution, or to find the best, if we can, approximate solution of the true image. And the goal basically is to design and analyze computationally effective mathematical methods, especially for large-scale ill-posed problems. And there are some challenges when we deal with large-scale ill-posed problems that I'm going to talk in a minute. Okay, so to do this, to do the inversion, so going from this blur and noisy image to a good approximation of the true image that we are looking for is actually a challenging task. And the reason why is because the problem is called ill-posed. And what does it mean to be ill-posed? There is no formal definition of a problem being ill-posed, but based on the definition from Hadamard, we have that the solution does not exist, the solution is not unique, or the solution does not depend continuously on the data. And each of those points over here is important, but in this talk we are interested in the last one. So what happens if our solution does not depend continuously on the data? So basically, if we have some stability issues. So if we have a true image over here, then the forward model would be like, because of some problems in the device and so on, or some noise, then we'll get a blur and noisy image. And you will say, okay, you can model this problem as a linear system of equation, then just solve it. But if you solve it, so basically if you do the inversion or the pseudo inverse of the operator, then you are going to get something that looks like this, that is nothing compared to the quality of the image that we are looking for. So basically we do not see anything here. So what do? We would like actually to determine the approximate solution by solving this linear system, the linear system of equation by solving this least squares problem over here. And one can just find the U naive that can be written as A dagger B, where B is B true plus E, that is the noise. And we can separate it in those two terms. Okay, the first term is fine because B true is in range of A and A dagger B true is bounded and it is nice and so on. But A dagger E actually causes issues because E is not generally in the range of A. So it can be arbitrarily large and it can corrupt the reconstruction. And so for the approximation that we get is not a useful approximation for the U true that we are looking for. So what do we do to solve this kind of issues? Then the big name over here is regularization methods, and we can just use regularization methods to solve it. When we talk about regularization methods, then there are different regularizations that we can do. So we can regularize with an extra term, or we can regularize by stopping the iterations early and so on. And I'm going to show here some typical behavior of a discrete ill-posed problem. So for example, if we have a problem like this, like a least squares problem, then it is very typical to see a behavior that is like this, that is called semi-convergence. So the RRE start decreasing, and then it reaches the minimum at some point, but then after that it starts increasing. So the question is, how do we deal with this? Then we will have to stop the iterations at the right place to get the reconstruction, or the best reconstruction that we could get. Moving forward, we can also discuss regularization methods that what they do, basically they substitute the ill-posed problem with a nearby well-posed problem, whose solution will approximate the solution of the original problem. So in general, I would write it as this kind of minimization problem when we have a P term and we also have a Q term over here. And depending on the P and the Q, then we get different forms of the functional that we are trying to minimize. Sorry, let me go back over here. So why do we want to use those values of P and Q different from 2? Basically, if we choose P equal to 2 and Q equal to 2, then we'll have just a Tikhonov regularization. But if we choose values of P and Q different than 2, then we have different forms. Then also sometimes the problem becomes more difficult, more challenging, and so on. But on the other hand, it will solve different issues that we might have in our data. So for example, if we choose values of Q that are different from 2, and especially from like less than 2, then in that case we are providing sparsity. So we basically want to have some sparse representation. While if we choose the value of P over here in the data feeding term, then the value of P different than 2 will take care of the different type of noises. So if we have just the Gaussian noise, then a two norm will do the work. Otherwise, we will have to find another type of norm. So in general, what we would do is that we want to approximate the 0 norm or the quasi-norm, 0 quasi-norm, but we cannot do that because the problem is NP hard and so on. So basically what we want to do, we want to approximate it with the best convex approximation. And if it's not the best convex approximation, we are going to show here in this talk that we can also do without a convex approximation over here. So going back to the minimization problem again, so we have this minimization problem for P and Q from 0 to 2, and here is an overview of the literature. So when P and Q equal to 2, then there is a very nice and rich literature for the classical Tikhonov regularization. And then when P and Q are from 1 to 2, then we have a convex minimization problem. And also when P and Q are from 0 to 1, then we'll have a non-convex minimization problem. Okay. Now, so basically what we are going to do is that we are going to every time that we have this kind of functional, then we want to majorize by a quadratic tangent majorant of the functional that we are trying to minimize over there. And here is the definition of what is called the quadratic tangent majorant. So in general, the functional that I showed before actually admits a quadratic majorant for values of P and Q from 1 to 2, but not for other values. So since it is not differentiable for those values, then we want to smooth it a little bit to find, to get a functional that we can deal with it easily. So, and then to make it differentiable, one smooth is the functional, and the popular version of this, the smooth function is given by this function here. So there is a nice, so let's describe very shortly the method proposed by Huang et al. So basically what they do, they introduce the smooth version of this norm, and after they introduce this, then consider the functional, and then the smooth minimization problem will become as the following. So basically the whole idea is like this, that any kind of functional that you are trying to minimize, and you at every point or at every iteration you majorize it and continue until you find the unique minimizer of the quadratic majorant. So now how do we do this process? Then we define the set of vectors vk and uk at each iteration, and also some other vectors that we call the weights. So this is w fidelity for the fidelity term and w for the regularization term. So basically these are weights for the fidelity term and for the regularization term, where all the elements here are element-wise. And in terms to the fidelity term, regularization term, and the weights for all those terms, the function now will look something like this. And this is going to be a quadratic tangent majorant for the functional that we are trying to minimize. Now, the minimizer of our tangent majorant, excuse me, is going to be computed by solving this minimization problem, where we define this mu here as this value, where epsilon actually is a user-defined constant, and then P and Q are the values that we will define for the regularization and also fidelity term. So an approximate solution can be determined by looking at a solution in a very lower dimensional subspace. So we run, so the idea is that in the beginning we run a Krylov subspace, we build that, so form an orthonormal basis for the solution subspace, and then after that we solve this minimization problem. How can we solve this? So we solve the minimization problem by computing the QR factorization. By computing this QR factorization, and then actually the QR factorization is not going to be expensive, even though your problem might be expensive, because we are actually projecting first in that smaller subspace at each iteration, and then we compute the residual. After we compute the residual, then we expand the solution subspace. So we start in general with a small solution subspace, and then by computing the residual at each iteration, we increase or define this matrix vk plus 1, and in general we will need to reorthogonalize to make sure that we get orthonormal columns. So related to models-based iterative methods, so these are kind of methods that if we have this M symmetric positive definite, then the non-negatively constrained quadratic programming problem is equivalent to this linear complementary problem that can be written like this. And here are some other theoretical results that I put over here just as a past background for modulus-based iterative methods. So from here, basically, I want to explain everything through the algorithm. So what we do whenever we have a linear system of equations, so what we want to do, we want actually to solve the constraint problem. And this is also the case for our method. So we define the omega 0, the first orthant, and we also define the indicator function over here. And then, so we want to solve this problem, but in general, it does not have a closed form solution. So we want to impose non-negativity by solving now instead this constraint optimization problem. And then how do we do this? So in the beginning, we define the generalized Euler subspace method with an initial dimension L, and we'll have this kind of factorization over here. After we have that, then we can create, or we can compute the QR factorization. And once we have the computed the QR factorization, then we consider now this general minimization problem. So we apply the modulus-based algorithm to solve this kind of problem. And let's say at some iteration, this is how the solution will look like. And here is the algorithm that expresses the non-negative LPLQ. So basically, we find the weights, and then once we have the weights, we iterate to find the non-negative solution, and then we increase the dimension and until the iterations converge. So I have two different versions of the algorithm, because at some point we can do better if we have some structure in the operator that models the forward problem. Then we can just do the FFT, and the algorithm becomes easier and also computationally cheaper. Now let's jump to the numerical example, since there is not too much time. So we would like to access the quality of the reconstruction. And in this case, we use the RRE, which is the relative reconstruction error, as a matrix L. In the regularization over here, we use a matrix W that is computed as a low pass filter and two high pass filters that have those corresponding masks here. And then the analysis operator is derived from these masks by imposing reflexive boundary conditions. After that, this is how the matrix W, W0, W1, and W2 will look like, and the big matrix W will be something like this. And actually, doing the computations with this matrix W is not very expensive, because this kind of metric is very large indeed, but it's very sparse. And we test the algorithm for different type of noise, as I said in the beginning. So we use Gaussian noise, we use impulse noise. When we have Gaussian noise, then in general, it's just a random vector that has it's Gaussian distributed with mean 0. And then in this case, so this is what we refer to the noise level. When we have the impulse noise, then the entries of the vector B are constructed by this formula, and sigma over here is also considered to be the noise level. How do we stop the iterations? So we stop the iterations when the relative reconstruction error, or actually when relative error of two consecutive iterations is less than a tolerance, like a outer tolerance or an inner tolerance, but we also set a maximum number of iterations that can be reached. And then we set the dimension. So this can be actually changed, but in all experiments, we set the dimension of the initial subspace L equal to 1, and then we continue in that way until the stopping criteria is satisfied. Here I show a numerical example. So suppose that we have a test problem over here. So this is the true image, and this is the PSF, that is a 26 by 26. This is the blur and noise contaminated image. We have 2% of the Gaussian noise and 20% of the impulse noise in the image. Then what we show over here, we actually compare with the non-negative LPLQ with the FFT in this case, because the operator has a structure. So here in the first from A, B, and C, we show from different noise levels of the impulse noise from 20, 30, and 40%. And then here is the plain LPLQ. So basically moving from solving the problem with that model-based iterative methods improve the quality of the reconstruction. We also show the quality over here for different noise levels, and also in terms of the RRE and then structural similarity for the Hubble test problem that I showed, and also some other tomography example. Now I want to show that actually this kind of method works also for real data. So we tested our algorithm for the walnut test problem. So we didn't have the true image, but we had the high quality reconstruction over here, and then this is the undersampled sinogram. So in the first, what we did is that here it is difficult to know how to also to define the regularization parameter at this point. So what we tried over here, we tried for different values of the parameter mu. This is the kind of reconstruction that that we are going to get. And in the same way, we express over here for the, this is the case for when we use the non-negative LPLQ, not with the FFT, but the generalized Krylov subspace, and we have 4 different noise levels, the values of the RRE and the structural similarity. Okay, so this is all for the talk today. Thank you very much for the opportunity. If you would like to look at the paper, here is the link that sends you to the paper. And thank you very much again for your attention.
Thank you for the great talk. Marcel, is there any question on Zoom?
No, we don't have any questions on Zoom.
Okay. Kathleen, is there any question on YouTube?
So I actually have a couple questions, but in the consideration of time, I think I will wait until the gather session.
Okay. Thank you again.
Thank you.